Right, today we're going to pull back the curtain on something that's running pretty much the entire automated world, but you probably never see it. We're talking about the hidden stopwatches inside of every factory, every machine. We're talking about PLC timers. Let's dive in. Just picture a massive factory floor for a second. You've got robots, conveyors, all these machines moving in what looks like a perfect synchronized dance. Well, that's not magic, and it's definitely not chaos. It's pure calculated precision. And all of that precision comes down to one simple thing: timing. You see, in the real physical world, things just don't happen instantly. Machines need a second to warm up, parts need a moment to settle into place, and safety gates need a delay to make sure everything is clear. That's where this idea of a digital pause button becomes absolutely essential. And these delays they're critical. For instance, you can't just flip a switch and start every single motor on a conveyor line at the same time. You'd cause a huge power surge. A heater has to, actually get hot before the process can continue. These aren't just nice-to-haves. They are fundamental requirements for making things work safely and efficiently. So the big question is, how do automation programmers actually control these little pauses? Well, they use one of the most fundamental tools in their entire toolkit, the PLC timer. The best way to think of it is like a super smart programmable stopwatch that lives right inside the brain of the machine. And when you boil it all down, that's really all a timer is doing. It's just watching for a condition, like, say, a button being pressed. And for as long as that condition stays true, it just counts. It's the simple foundational block for all that complex timing we were just talking about. Okay, so let's break down the parts. The preset is your target. Let's say you want to time for 10 seconds. The accumulated value is just the current reading on that stopwatch as it's counting up. The enable bit, that's basically the start button. And the done bit, well, that's the little alarm that goes off when the accumulated time finally hits the preset. See? Pretty simple when you think about it like that. But it's not a one-size-fits-all situation. In the world of PLCs, there are really three main types of timers, and each one is like a specialized tool designed for a very specific job. So let's meet the team. First up, we've got the rockstar, the most common one you'll ever see, the on-delay timer, or TON for short. I love to call this one the wait then go timer, and you're about to see exactly why. So the key thing to get here is that the action happens after the delay. The input turns on, the timer starts counting, 3, 2, 1, and then the output turns on. But here's the catch, and it's a big one. If that input turns off at any point before the timer is done, the whole thing resets back to zero. Nothing happens. And a perfect real-world example of this is a motor with a delayed start. You press the start button, which kicks off a tongue timer. It counts for 5 seconds, and only when those 5 seconds are up does the motor actually fire up. It creates that crucial pause before the action begins. All right, now for our next tool, the off-delay timer, or TOF. This one is my keep going for a bit timer, because its logic is pretty much the exact opposite of the one we just saw. See the difference? With a TOF, as long as the input is on, the output is on right along with it, instantly. The timer doesn't even start doing its job until the input signal goes away. The second you turn the input off, the countdown begins, keeping that output running just a little bit longer. And this makes perfect sense for something like a cooling fan on a big machine. The machine's on, the fan's on. But when you shut the machine down, you need that fan to stay on for, say, another 10 seconds to get rid of all that extra heat. That is a textbook job for a TOF timer. So let's just put them head to head. The TON times as long as its input is on, creating a delay before something starts. The TOF, on the other hand, starts timing when its input turns off, creating a delay before something stops. It's a simple distinction, but man, is it powerful. Okay, our final tool is a really special case. This is the Retentive Timer, or RTO. And you can think of this one as the never forgets timer, because unlike the others, this one has a memory. And this is the game changer. If you start an RTO and the input signal goes away, the timer doesn't reset. It just pauses. It holds its value. When the input comes back on, it picks up counting right where it left off. The only way you can ever get this timer back to zero is with a completely separate reset command. And you can probably already guess why this is so incredibly useful. It's perfect for tracking total operational hours on a piece of equipment. Every time the machine runs, the RTO adds to the total. It doesn't matter if it runs for 5 minutes today or 10 hours tomorrow, that timer keeps a running tally, letting you know exactly when it's time for maintenance. So we've met the individual players, we have our three tools. Now let's see how they work together to conduct a real-world process, kind of like a perfectly timed symphony in a bottling plant. Okay, check this out. A sensor sees a bottle arrive. Right away, a ton of timer kicks in for just 1 second to make sure the bottle has stopped in the perfect spot. Then another timer opens the fill valve for exactly 3 seconds. No more, no less. Then a final tiny half-second delay from another ton makes sure that valve is completely closed before the conveyor starts up again and moves the bottle along. It's just this beautiful cascade of timed events. So you can see, understanding these timers isn't just some academic exercise. For the programmers and technicians out there, using them correctly is what makes the difference between a reliable, smooth-running machine and, well, a chaotic mess. And here are just a few pro tips. Give your timers clear names, like bottle_fill_timer, not some cryptic code like T40. Leave a comment explaining what it does. Don't use a timer just for the sake of it if a simple sensor would work better. And please always double-check that your preset times are actually correct for the job. And that really is the bottom line here. These seemingly simple instructions are an absolute cornerstone of modern automation. Knowing how they work, which one to use for which job, and how to use them well, that is a totally non-negotiable skill for anyone in this field. So I'll leave you with this thought. The next time you're stopped at a traffic light, or riding in an elevator, or using a microwave, just think about those invisible little stopwatches inside, counting down, making it all happen seamlessly. What other automated systems in your own life are secretly being run by these digital clocks?